Okay, now if you have alternating current, where you have a sine wave here instead of a square wave, the same type of phenomenon occurs, but you don't have the sharp changes in the current, and your curve doesn't have the sharp, your voltage of the capacitor voltage curve doesn't have the sharp changes because you don't have sharp changes in the source voltage. What happens is, if you start with source or capacitor voltage 0, the source voltage is going to chase the capacitor voltage is going to chase the source voltage. It's going to stay less than the source voltage, but the source voltage, first of all, there's no source voltage at the very instant that you start, but then very soon you build source voltage, and you build it kind of fast. So the capacitor voltage is going to chase the source voltage until the source voltage reaches its peak, and then we'll see what happens. So the capacitor voltage chases the increasing source voltage. Now, since the source voltage is increasing, you don't have an exponential approach to a constant source voltage. So your capacitor voltage continues to increase, the source voltage peaks, but the capacitor voltage is still going to have a greater voltage to chase until the capacitor voltage curve meets the source voltage curve. So the capacitor voltage is going to continue to increase up to the point where you have an intersection. And at that point, it's going to be its maximum because immediately the source voltage is going to be less than the capacitor voltage, so the capacitor voltage is going to chase it back down. And that's going to happen like so. It's going to chase on down here, and you're going to kind of, until, again, the capacitor voltage reaches the source voltage, and then it's going to chase the source voltage back up in a very similar manner. And you will have this phase difference between the source voltage and the capacitor voltage. Also, the capacitor voltage will never be as great as the source voltage because it never has time to actually reach it. Same as over here. Okay? So now we have this phase difference between here and here. That's not the difference that we're really interested in. What we're really interested in for right now is the difference between the current through the source, through the system, and the, let's say through the capacitor. That's actually a displacement current, but we're not going to get too specific with that. So how does the capacitor voltage relate to the current? So we'll do that in a minute as soon as I find my red chalk, which appears to be missing. Okay, I found my red chalk and realized I don't need it. I'm going to do the current in yellow. So let's see what happens to the current. Okay, well, when we begin, we immediately have the source voltage. There's no voltage on the capacitor, so we are going to have some sort of a current. But the source voltage isn't very big, so we're not necessarily going to have a whole lot of current. But then, as the source voltage builds, well, you're really being driven by the difference between the source and the capacitor voltage. The source and capacitor voltage continue getting further and further apart up to this point, and then they start getting closer together again, or at least shortly after this point, so that the current is going to increase up to about this point, but then the capacitor voltage opposing the source voltage is going to start getting closer to the source voltage because the source voltage is decreasing while the capacitor voltage is still increasing. Now, we don't want to get into the details of how that works, although it's something you would do well to think about. But then the current, which is driven by the difference in these two voltages, is going to start decreasing at this point. And when you get to this point where the capacitor and source voltages are equal and opposite, the current's going to have decreased to 0. So at this point, the current's going to be 0. And then at this point, the current's going to be 0. Now between here and here, the current's going to go down to some minimum, but then it's going to return to 0 when we get to this point. And you can think about the details of that. It's going to go like this. And then we're going to come up to a maximum current until we get to 0 current here, and we're going to have another peak. So here's how our current is going to develop in comparison with our source voltage and our capacitor voltage. Now, in terms of both models, it's pretty easy to see once you've played around with these models and thought through it a little bit that the current is going to reach 0 before the capacitor voltage reaches 0. And here again, the current reaches 0 before the capacitor voltage reaches 0. There are easier ways to show that it must be so. We can simply take the derivative of the capacitor voltage, which in this case, in the case of AC, is just a sine function. If it's a sine function, then the derivative is a cosine function. So the current being a cosine function legs the sine function. But we want to really be able to see this in terms of what's really going on in the circuit. And then we want to be able to represent this by a phasor diagram. Now on the phasor diagram, we're going to let the current be represented by the yellow vector. We've used yellow throughout to represent current. And then we're going to let the voltage be represented by the orange color. And we see that the voltage reaches 0 after the current does. Now, let's just think about what this model says about the current. In this model, the current is moving, and we've got an angular velocity, omega. Okay. Again, this is for an AC. It's not for this. This model only applies to sine and cosine function. And the differential equations are going to tell us that we have sines and cosines, and we'll look at those. We already have to an extent. So we have some angular frequency omega of the source, which is going to drive the current at the same angular frequency. So the current is changing at angular frequency omega, which means that this vector is going to go around this circle with angular frequency omega, period, omega over 2 pi. Again, I'm assuming that you understand the model for simple harmonic motion, the reference circle model. And this is only a model. This is not an actual current here. This is actually the reference model of the vector current. The actual current is going to be represented by the projection of this vector. And I'm going to use a lowercase I of t. And I should have done that up here. So I'm going to stop and relabel that and explain that very quickly. Okay, I've made the change here, and I made it here as well. The current I of t, the actual current in the circuit, and using the lowercase I to indicate the time varying current. The I of t vector goes around the circle, and this projection is maximum, so you have maximum current, then it reaches 0 as we move from here to here, and so you have minimum 0 current, then it goes to negative, which is your minimum, which is over here, and then back to 0 and back to maximum. So we understand how the current, the time variation of the current is modeled by the idea of a point moving around the reference circle, or a current vector moving around the reference circle. Now, we've seen that the voltage lags the current. The voltage hits 0 after the current reaches 0. So we want a voltage vector on this picture as well. Now, the voltage vector I'm going to draw with a different magnitude. It could be larger, could be smaller, but I'm going to make it smaller just because it messes up the picture a little bit less. And we have this angle between the current and the voltage vector. So this is your current vector, here's your voltage vector. And we have an angle which we could call phi or theta naught. I've used both. So that's this angle in here. Okay, you can't see that. The angle is labeled, the angle is indicated in the counterclockwise direction, but the angle here from current to voltage would actually, if you go from here to here, would actually be a negative. Not too important right now. We'll fine-tune that idea shortly. So that as these two vectors rotate around the reference circle, we have a current vector and we'll have our voltage vector. Now, I can't draw that up here, it's kind of, but we see that this voltage vector projects down here, so we have our V of t. I'm going to call this the vector that rotates around the reference circle. These vectors don't really exist. They're just mathematical conveniences to allow us to visualize how the current and the voltage relate. So you can understand now, as both of these rotate around the circle with the same angular frequency, the current is going to reach zero when the voltage is still over here a little bit. And then the current is going to maximize before the voltage does, and so forth, giving you exactly the behavior that we see here.